700 applications to bioengineering, and we do our best to find the best 50 or so people who we think are going to be the future leaders of the field. Some of them come in and they're like, yes, I'm the future leader of the field. They're fine, they're kind of annoying people. Melissa was not one of those. She was worried that she had somehow got in by mistake and wasn't fully confident in her abilities. And one of the exciting things about being an advisor is you see students build their confidence, build their competence, and she has really done that over the course of her PhD. She is extremely strong technically, and beyond that, she's able to engage in a number of different disciplines in a way that you very rarely see. She's become a leader in the lab. She's become a leader in bioengineering at Stanford. Frequently, I will meet a faculty member in the medical school, and I get around. I know a lot of people that are like, oh yeah, I heard about your stuff. I'm like, from who? Melissa Boswell. She is a leader in the International Society of Biomechanics. And in fact, she and Hannah, the Boom Girls, are famous. You know, when you get as old as me, I go to biomechanics meeting and occasionally people are like, oh my God, there's Scott Delp. I was walking around a biomechanics meeting and Melissa walked by and was like, there's one of the Boom Girls. So she is an international biomechanics superstar. This meeting is being recorded. Okay, Melissa, I will not embarrass you anymore because we want to jump right to understanding what you've done in your thesis. You're in for a treat. It's really excellent work spanning many fields. So I'll turn it over to you. Yeah, otherwise,
Scott breathing. Oh, well, thank you so much for that awesome introduction, Scott. And thank you to everyone who's here and everyone on Zoom too. I'm really excited to share my thesis work on that focuses on enabling large-scale access to biomechanical assessment and improving mobility. So movement is an essential part of human existence, not just for maintaining our physical and our mental health, but also to express ourselves and connect with each other and the world. Throughout our life, though, our mobility can change. It can improve in speed, flexibility, and strength, or other times it can be restricted by things like injury or neuromuscular diseases and disorders. Knee osteoarthritis is one such neuromuscular disease that can limit mobility and currently poses a massive global burden. My clicker isn't happy right now. There we go. So knee osteoarthritis is a condition that's characterized by the degradation of the cartilage at the ends of the bones. When the cartilage wears away, this can expose the underlying bone, resulting in bone spurs, as well as significant pain and stiffness. Knee osteoarthritis affects over 90 million people globally, with a 45% chance of development in one's lifetime. Patients with osteoarthritis often have comorbid conditions such as heart disease. They have lower levels of physical activity, and they have higher levels of depression and anxiety than those without osteoarthritis. So while we often think of it as a joint disease, it's truly a multifaceted disease that affects an individual in all aspects of life. Unfortunately, there's no known cure for osteoarthritis, so developing treatments to manage symptoms and slow progression is a grand challenge for the field. The typical treatment trajectory is to start by suggesting lifestyle changes such as anti-inflammatory diets and exercise, as well as anti-inflammatory medications, steroid injections. And if those fail to help, then a total knee replacement or arthroplasty is the main surgical option. Unfortunately, lifestyle changes aren't always used or adhered to, and patients end up moving more quickly through this treatment trajectory towards injections and surgery. And I believe there's a key step missing here that could improve this treatment trajectory, which is assessing one's biomechanics. So from a biomechanical perspective, we know that overloading the knee joint is a contributor to osteoarthritis. And evaluating the biomechanics of the joint, we can design more effective ways for people to move where they can continue to stay active, but reduce the forces going through their knee. And this can improve pain and even slow osteoarthritis progression. However, biomechanical assessments have traditionally been limited to a laboratory that's equipped with retroreflective markers, which we attach to a participant, multiple cameras, which can track the location of those markers in space, and force plates, which capture the ground reaction forces that occur when a person's in contact with the ground. So this expensive and technical equipment isn't scalable for the tens of millions of people with osteoarthritis. So there really is a large need to develop tools, digital tools that enable biomechanical assessments at a large scale. And if we can do that, then perhaps we can prevent or prolong the need for medications and surgery and insert biomechanical intervention as an additional step in osteoarthritis treatment. And in my work today, I'll share tools that can help make this a reality. And I'll also propose that these same tools can be coupled with psychological intervention to change mindsets and therefore make lifestyle changes more likely as well. So that biomechanical intervention and lifestyle changes together can form a more holistic and healthy treatment plan for individuals with osteoarthritis. So the overall goal of my thesis was to develop these tools and methods that can improve access to digital biomechanical assessments for individuals with knee osteoarthritis that take a more holistic biopsychosocial approach. In the first part of my defense, I'll talk about a project that demonstrates the feasibility of personalized biomechanical intervention for osteoarthritis with a smartphone camera. Then I'll share a second study where I evaluate the psychological construct of mindset in people with knee osteoarthritis and evaluate how it relates to the use of movement for symptom management, which could influence engagement with digital tools. And then finally, I'll share a third project in which we developed a platform and protocol to deploy a nationwide at-home biomechanics study that can detect osteoarthritis with just a smartphone camera. And I'm really proud to share that 2 of these studies have led to published papers and a third manuscript that's currently in preparation. So I'll start first with our work towards a mobile personalized biomechanical intervention. So as I mentioned, overloading the knee joint is a contributor to osteoarthritis. But the way to directly measure internal joint forces requires an implanted sensor, which is intrusive and not feasible for an arthritic knee. A surrogate measure for internal knee loading is the external knee adduction moment. So this moment occurs in the frontal plane and rotates the tibia with respect to the femur. And if we take a look here at what this means in the joint, you can see here that this rotation of the tibia creates a force in the inside of the knee or the medial knee compartment. And studies have shown that the peak knee adduction moment is related to the presence, severity, and progression of medial compartment knee osteoarthritis. Pete Scholl and colleagues found that in many patients, learning how to walk with a reduced foot progression angle, so walking with your toes further in, can reduce the peak knee adduction.
Live from my backyard where I am smoking a brisket and some ribs. I'm making meats now, smoking these meats here. Our little meat smoking. It's smoking. So I'm the meat chef. Yeah, someone asked me, do I smoke meat? Smoking meat, smoking these meats. Smoking meats earlier in the day. Smoking these meats, just set the charcoal up and you set the wood chips up, and then smoking meats, grilling meats, good smoky flavor. Smoke a brisket for like 12 hours. You just smoke lemon chicken, smoke salmon, you'll love it. Bison sirloin, ribs and sausage, so I'm looking forward to that.
Walking with their toes pointed further out to decrease their knee adduction.
Today we got a brisket on the big guy, and some pork ribs on the green egg. Meat like a
and then we calculate the knee adduction moment with a physics-based approach using inverse dynamics. And from that, we can then determine the foot angle that most effectively reduces the knee adduction moment. So while changing the angle of one's foot during walking is a simple, easily adoptable, and effective strategy, it currently requires a full biomechanics lab. But in recent years, there has been tremendous growth in tools that enable biomechanical measurement outside of the lab. So inertial measurement units measure linear accelerations and angular velocities. Wireless electromyographic sensors can measure muscle activation. Shoes can be instrumented with pressure sensors that can measure the center of pressure and shifts in weight. And pose estimation algorithms predict the location of joints from 2D video. And this motion analysis from 2D video is a particularly exciting opportunity because 84% of the global population owns a smartphone and could access their own pocket-sized tool for quantitatively self-assessing movement. So here's a video of the pose estimation algorithm open pose in action. And you can see here that these algorithms have been used to make fun videos like these, and on average, accurately detect poses and the locations of people. But are they accurate enough for medical applications? And in our study, we wanted to know, are they robust enough to enable real-world measurements that give people insights into important health-related measures like the knee adduction moment? And if yes, then we could use smartphones or low-cost video cameras to develop widely accessible and low-cost approaches to personalizing foot progression angle modifications. And we propose that the joint location from these algorithms could be input into a machine learning model that could then predict the knee adduction moment and the most suitable gait modification. But we currently don't have data sets with simultaneous 2D video and motion capture that could train a model to do this. So as a first step towards this vision, we instead decided to try the same approach, but with using motion capture marker positions as an input to a machine learning model that predicts the peak knee adduction moment. And so we built 3 models with slightly different inputs. The first model used 3D motion capture marker positions, while the other 2 models projected the 3D positions into either the frontal or the sagittal plane to replicate joint positions that you would get from 2D video. We predicted the peak knee adduction moment during each step and use those peak values to also evaluate the clinical tasks of determining peak knee adduction moment changes with varying foot progression angle modifications. So our data set was from in-lab studies with participants with and without osteoarthritis, walking naturally and with foot progression angle modifications. And we split the data such that our test data contained participants that the neural network hadn't been trained on. And when we evaluated our model on this test set, we found that the model with the 3D position inputs accurately predicted the peak knee adduction moment with an R-squared value of 0.78. And similarly, using only the 2D positions from the frontal plane, we obtain an R-squared value of 0.85. So the results from the 2D model are shown on this plot here. On the x-axis, we have the normalized peak knee adduction moment from inverse dynamics. And on the y-axis here, we have the predicted peak knee adduction moment from our machine learning model. On this plot, each point is a step, and each colored cluster of points represents a set of steps from a single subject. And you can see in this plot that for some participants, our model did consistently overestimate the knee adduction moment, but we do see a linear trend here, which indicates that perhaps which is important for classifying changes in the knee adduction moment, which we also tested for, and I'll present next. But I did want to say that these results are similar to, if not better than, studies aiming to predict the knee adduction moment from ground reaction forces and anthropometric measures and force instrumented shoes and inertial measurement units. However, predictions from 2D video would be cheaper and require less equipment than with force plates or an inertial measurement unit system. So here are the results that test how accurately our model could classify changes in the knee adduction moment with toe in or toe out foot progression angle modifications. So a perfect prediction would be along the y equals x line, but the goal of our classification problem was to predict an overall increase or decrease in the knee adduction moment. So to get the points either in this top right or lower left quadrant. And our model had 92% accuracy, which means that if we were to use it to select a personalized foot angle that reduces the knee adduction moment, we would be right 92% of the time. So one limitation of our study is that we trained on a single data set in one biomechanics lab and on a treadmill. Every biomechanics lab and clinical setting are different in both their setup and the equipment they have, so our model may benefit from training on additional data from various sources. And in the future, we'd like to use video as the model input, but our study is a good first step towards showing that it may be feasible to one day have an app where a clinician could take videos of their patients walking with different gait modifications and see which one would maximally reduce knee loading for each individual patient. So this study was published in Osteoarthritis and Cartilage in 2021, where I was the co-first author with Scott Ulrich. And we also made our code and data set publicly available so that other researchers can try to train more accurate models or models that predict other gait parameters. So in the Human Performance Lab here at Stanford, we conducted a clinical trial on personalized foot progression angles for osteoarthritis that was led by Scott Ulrich. And my desk was located in this open space. And while I would never intentionally listen in on conversations happening, I couldn't help but overhear the conversations between our research team and the patients. And what really stood out were the differences in views about osteoarthritis and expectations about the intervention and motivations to engage or not engage with physical activity. And in hearing these, I realized that even though we can make biomechanical interventions digital, and those would perhaps reach more people, it doesn't necessarily mean that an individual will use them or be more physically active because of it. So this made me really curious about how these thoughts about osteoarthritis and exercise may actually influence one's relationship with movement. So in the second study, we sought to better understand how psychology influences engagement with exercise. And this part of my work occurred in two phases, with the first being to understand mindsets about exercise, and the second being to improve them. So how might one's thoughts and beliefs be influencing participation in physical activity? Well, physical activity levels may be low in individuals with osteoarthritis because they face this unique challenge of joint pain, swelling, stiffness, and functional limitations, as well as misconceptions about physical activity as it relates to their osteoarthritis status. So for example, individuals with osteoarthritis may know that consistent exercise is beneficial long-term, including improving pain and function and quality of life. And they don't want to feel limited or restricted in their activity, but they have to balance these thoughts with the information that osteoarthritis is due to wear and tear, which leads to the common misconception that further activity may quicken this wear. And these thoughts and beliefs, along with one's experiences and social interactions, inform an individual's mindset. The definition of mindset is core assumptions about a domain that orient an individual to a particular set of attributions, expectations, and goals. We have mindsets because the world is complex and subjective, and mindsets help us understand the world and its uncertainties. They help us predict what may happen so that we can choose our behavior or how to act. And this definition and understanding of mindset was developed by Dr. Leah Crum, who is an expert in unpacking the ways that our mindsets affect our health, and advised me on the following projects. For example, one study by Leah Crum and Ellen Langer found that informing hotel housekeepers that the activities that they performed at their job satisfied recommendations for a healthy lifestyle actually led to higher levels of perceived exercise, as well as weight loss and a reduction in blood pressure, even without an increase in objective physical activity level. And in addition to our mindset about our perceived exercise level, we also have a mindset about how enjoyable we find exercise. So to better understand this mindset, we can quickly reflect on what comes to mind when you think about exercise. So what types of words would you use to fill in the sentence, exercise is blank? And you may include things like boring, unenjoyable, stressful, tiring, painful. Or you may include things like fun and enjoyable, refreshing, strengthening, connecting. And these thoughts and beliefs actually make up your mindset about the process of exercising. And while it's not right or wrong, it does have an impact. And we can quantitatively measure how enjoyable exercise is to people through the mindset about the process of exercise scale. So this mindset is defined as the extent to which individuals associate the process of engaging in exercise behaviors with appealing qualities like easy and pleasurable versus less appealing qualities like difficult and unpleasant. The process of exercise mindset is a 7-question, 1-factor scale developed and validated by Daniel Bowles and colleagues, and it demonstrates strong internal consistency and test-retest reliability. And Danielle Bowles has shown in her work that in students, the process mindset can be improved, and it's also associated with health status and predicts physical activity involvement. Mindsets have not been evaluated in the knee osteoarthritis population, but understanding and perhaps even intervening to improve mindset and the appeal of physical activity may increase physical activity participation. So to test our hypothesized relationship between mindset and physical activity, I conducted an online survey of 150 people with and 152 people without knee osteoarthritis. So this survey included the process of exercise mindset measure, which is shown here. It also included measures of health, osteoarthritis symptoms, and physical activity, as well as an open-ended question about how they manage or improve their osteoarthritis symptoms, which is shown here. And their survey was repeated 3 weeks later. And we found that people with knee osteoarthritis had a less enjoyable exercise mindset than those without osteoarthritis. However, after controlling for gender, age, BMI, health, and physical activity level, having osteoarthritis was no longer a significant predictor of one's mindset. And instead, in this model, only higher health and physical activity scores were related to a more enjoyable exercise mindset. We did find that mindset was correlated with future physical activity. So you can see here that higher physical activity scores were related to a more enjoyable exercise mindset. And this relationship was consistent even when controlling for demographics, health, knee pain, and stiffness with a coefficient of about 39. And since we standardized the continuous independent variables, this result means that a 1 standard deviation increase in the process exercise score was associated with an increase of almost 39 points in our physical activity scale, which was the physical activity scale for the elderly. And for context, an example of a 39-point increase would correspond with an increase in performing physical activity for 2 to 4 hours per day, seldomly to often. We found that 50% of participants with knee osteoarthritis reported using medication or injections to manage their osteoarthritis symptoms, while only 27% reported using physical activity. And when comparing mindsets across these groups, we saw that people who use exercise alone or people who use exercise and medication to manage their symptoms has significantly higher or more enjoyable exercise mindset than those who use medication alone to manage their symptoms. But we didn't see any significant difference between those who use exercise and medications and injections or exercise alone. So in summary, while joint pain, functional limitations, and maladaptive misconceptions about knee osteoarthritis may negatively impact the mindset of an individual, mindset doesn't necessarily depend on osteoarthritis status. Some individuals hold a more enjoyable exercise mindset, which supports the potential for improving mindset. Further, mindset about physical activity was associated with future physical activity level and related to an individual's chosen symptom management strategy. So this study was published in Annals of Physical Rehabilitation and Medicine in 2022, and the data set and code in this study are also publicly available on SimTK. So this survey study helped us to better understand mindsets, but what we really want to know is how can we improve them? There are currently few psychological interventions for knee osteoarthritis, but the most common ones, such as cognitive behavioral therapy, are currently developed as in-person trainings by professionals that are completed over many hours and sessions, which is expensive and not scalable. So in addition to an effective mindset intervention, we also wanted to develop something self-guided and digital, brief, inexpensive, and thus scalable. So to develop a digital mindset intervention, I organized a team of experts across many different disciplines. So we had many experts from psychology, mechanical engineering and bioengineering, orthopedic surgery, narratology, and even individuals with osteoarthritis, which included Zoom interviews that I had with people with osteoarthritis to better understand their experience and the language around that, as well as 3 individuals who helped us create the intervention content and participated in the filming of the videos, which I'll share in a minute. So together we developed the program Rethinking Osteoarthritis. This program has 4 modules, each with a series of short films and reflective activities. And throughout the series, I help narrate and guide individuals through the program. And then in each module, we have experts on the topic share the latest research We have individuals with osteoarthritis share their experience, and we use animations and positive videos of movement to help instill the ideas that we're conveying. So module 1 aims to help individuals better understand osteoarthritis and common misconceptions surrounding it. So I'll play a short clip from our intervention, and I also included an example of one of the reflection questions that a participant would get after they watch these films. So Stanford orthopedic surgeon Nick Giori helped to lead this module. There are a few reasons for misconceptions about pain. Maybe a friend or family member with osteoarthritis shared their painful experiences, or an advertisement for arthritis medication highlights its painful nature. Hearing this can change your expectations of pain, leading to increased sensitivity to pain signals.
In our culture, we tend to rely heavily on imaging to explain symptoms. But the fact is, the severity of osteoarthritis on X-ray or MRI does not correlate that well with pain that one experiences. There are many examples of people with osteoarthritis on imaging who have low levels of pain and high physical function.
So module 2 teaches what type of exercise is beneficial for improving osteoarthritis symptoms and joint health, as well as the many benefits of movement even beyond helping with osteoarthritis. And bioengineering professor Scott Delp helped to lead this module. Module 3 targets the process of exercise mindset and presents the opportunity to rethink physical activity as something that we want to do because it is fun and social and relaxing as opposed to boring or stressful. And PhD student Chris Evans, who is an expert on mindsets about health and mindfulness, led this module. And then in the final module, we take what we call a meta mindset approach, where we talk about what mindsets are, why they are important, and how to adopt more helpful mindsets about osteoarthritis and exercise. And in this module, we tie everything together and explain that throughout the program, we've actually been presenting different mindsets about exercise and osteoarthritis. And while they are not right or wrong, they do have an impact. And psychology professor Aaliyah Crum led this module, which I'll also show a quick clip of.
But the important thing to remember is that the mindsets we hold or choose to hold can make a difference. So empowering yourself with a mindset that osteoarthritis is manageable or even an opportunity can help revitalize you with energy to engage in the tools you need to manage your osteoarthritis. And as a result, your body can become inspired to function as well as it can and improve your overall health.
The advice I would give to someone recently diagnosed with osteoarthritis is that it doesn't define them, and to think about it as a new opportunity to try new activities that they might not otherwise have tried.
So we actually piloted this digital Rethinking Osteoarthritis program with 21 individuals with knee osteoarthritis across the US. And we found that individuals' knowledge about osteoarthritis significantly improved by the end of the intervention. So this scale was developed by Professor Ben Darlow to measure knowledge about osteoarthritis in individuals with knee or hip osteoarthritis. It scored from an 11 to 55, and on average, participants in our intervention increased in this scale by 12 points. I also added some direct quotes from participants to add some color to thoughts that might have been associated with these scores. So for example, one individual initially felt that there is nothing that could be done about osteoarthritis, but after the intervention felt encouraged and motivated that they could enjoy an active lifestyle that emphasizes low impact. Individuals' exercise mindset significantly increased to a more enjoyable mindset about physical activity by an average of about half a point. And for reference, a previous study by Danielle Bowles found that in students, just a 1/10 of a point higher process mindset score led to higher fitness class attendance. And an example here is one participant who initially felt that exercise should be exhausting and not pleasurable, but then after the intervention realized that exercise can be more about the feel-good effects of getting outdoors in nature and keeping the body moving. We also measured mindsets about osteoarthritis. So this is a mindset that's based on the broader illness mindset inventory, which is a scale developed and validated by Sean Zion that measures the extent that one views chronic illness as a catastrophe versus manageable or even an opportunity. And I adapted the scale by changing chronic illness to osteoarthritis in the survey items. And this scale is scored from a 1 to a 6. And in our study, we found that individuals' osteoarthritis mindset significantly increased to a more adaptive mindset about osteoarthritis by an average of 0.9 points. And you can see that here from this individual who initially said that our arthritis is the end of quality of life, but then at the end felt that for the first time, they're hopeful that they can return to an active lifestyle and have empowering ways to help them. On average, participants strongly agreed that the program was accurate, enjoyable, helpful, and relevant, and agreed that the information presented was new, which makes us optimistic that this will be beneficial for individuals with knee osteoarthritis. And I wanted to share a short clip from some interviews with participants to add some more color to their reactions to this intervention.
Before, I've been thinking that very soon surgical intervention might be inevitable, but there are things that you can do. You know, you can keep active, try to keep yourself social and keep a positive mindset. And that's, I think, what gave me a more positive outlook.
Exercise done correctly is not going to worsen it. That was another big thing that I learned from that. Rather than exercise, think of it as play, fun. You're engaging your body in a good way.
You know, you think about it to yourself, oh man, this is gonna get worse. But that was me doing that to myself. And that part of what the video said about your mindset. Once your mindset got right, I'm like, no, I'm still pretty good. I'm still can do this.
I think the videos have really helped me with my mindset, and that I'll be able to change my mindset and exercise and become healthy and strong as I need to. So in 6 months, I'll drop you a line and say, guess what? No surgery. Guess what? I'm hiking up and down those hills.
So this was really exciting to see, and we felt that the intervention does show promise that mindsets about osteoarthritis and exercise can be changed. And I'm really excited to continue working with our awesome team in planning a randomized control trial to test if these changes in mindset lead to improvements in physical activity and perhaps osteoarthritis symptoms, as well as how they may change over time. Our sample size was quite small in this pilot, so it'll be helpful to have a larger study sample as well as a control condition to compare our intervention to. But what's been really exciting about this study is that it is completely digital and self-guided, which makes it a cheap, accessible, and easily scalable intervention for anyone diagnosed with knee osteoarthritis. So now I've talked about two different digital interventions, one for biomechanical intervention and one for psychological intervention. Typically, the outcome measures for biomechanical interventions are measured in a lab, and psychological intervention outcomes are measured with surveys. But in order to objectively measure the effects of these outcomes or these interventions, we need a digital quantitative means to measure physical function. And so in the final study that I'll present, we developed a mobile platform and algorithm for quantifying a functional test with only a smartphone. So sit-to-stand transitions are widely used in clinics to test physical function by measuring time to complete the test with a stopwatch. However, movement is a key strategy or key determinant of sit-to-stand strategies. And in-lab studies have shown that kinematics, such as joint angles, can give additional health insights above timing alone. So because of this, we chose to focus on the most common variation of the sit-to-stand test, the 5-repetition sit-to-stand test, where an individual goes from sitting to standing 5 times as fast as possible with their arms crossed in front of them and their feet flat on the floor. The goals of our study were to first develop an online tool to capture and automatically analyze self-collected at-home videos of the 5-repetition sit-to-stand test and deploy it in a nationwide study. Second, we wanted to validate the tool for previously determined relationships between sit-to-stand parameters and demographic and health measures. And then finally, we wanted to leverage our large data set to explore new relationships between sit-to-stand parameters and additional demographics and mental health. So here is an overview of the study. It started with participants collecting a video of their sit-to-stand test at home using a smartphone or tablet. The video was uploaded to the cloud, and the computer vision algorithm OpenPose detected joint locations throughout the movement. Then our machine learning tools computed the key transitions of when the participant rises from the chair and returns to sitting. And in addition to time to complete the task, we also computed key biomechanical parameters like trunk flexion or how far forward a person is leaning as they're going from sitting to standing. So from the user side, this looked like going to our website, sit2stand.ai, to join the study. They completed a series of questions to make sure it was safe for them to participate. They got a video and a written description of the test instructions, and then the option to either record or upload the test. And then during the recording, they were instructed to have another person record them 5 to 10 feet away at a 45-degree angle. The video played back for their approval before submission. They were immediately directed then to a health survey. And then at the end of the survey, they were given their video with the pose estimation results overlaid, which we found participants really enjoyed receiving at the end of the study. So we had 471 individuals complete the study entirely self-guided across 34 US states. Because of the accessibility of the study, we were able to collect a diverse sample. So in the 387 participants that were used in the final analysis, the age of participants ranged from 18, which was the minimum age to participate, to 95 years of age. We had a range in BMI from underweight to obese. We had about an even distribution of males and females, and also a range of different ethnicities. So here are the many different videos we collected from across the country. It was really amazing to see so many people participate from their living rooms, their kitchens, and even outside. And from these videos, you might be able to find some of yourselves in here. But we get a glimpse of the many different ways that people perform the test. And I'll zoom in on a few examples of these different movement strategies. So in this first video here, you see an individual who has a lot of control during the sit to stand test and is able to go up and down pretty easily. And we can compare this to an individual who tends to lean further forward a bit more and use their momentum to get off the chair to come up to standing. And actually, this individual has knee osteoarthritis, which I'll talk about in the results. We also saw participants who did focus on doing the test as quickly as possible, and so lean further forward, not necessarily to use their momentum to get up, but to be able to go up and down as quickly as possible. And then we have participants here who had a combination of these different movement strategies, and I'll show this video with the sound on because it's kind of fun to hear what's going on as participants are doing this. So it always kind of brought me some joy to like hear some chuckling during these. I'm not sure how that affected the study, but hopefully positively. So we first compared the results of our study to results of past in-lab studies. And similarly, we found that longer times to complete the sit to stand test were associated with older age, which is shown in this plot here, as well as a higher body mass index and lower physical health. Oops. We also found that larger maximum trunk flexion when going from sitting to standing was associated with osteoarthritis presence, even when controlling for age, sex, BMI, and time. So individuals with osteoarthritis in the knee or hip tended to lean further forward when going from sitting to standing than those without osteoarthritis. And these results indicate that kinematics may give additional information about health and functioning or particular diseases such as osteoarthritis than timing alone. And a larger trunk flexion among those with osteoarthritis does make sense from a biomechanical perspective. So compared to a normal sit to stand transition here, if an individual is leaning further forward during sit to stand, this reduces the distance between the knee joint and the ground reaction force. And when that happens, it actually reduces the knee extension moment, which an individual with osteoarthritis may want to do as they tend to have weaker knee extension muscles, or they may be compensating for pain in the knee during standing. And with a link segment model like the one shown here, studies have found that a 20-degree increase in trunk flexion reduces the knee joint moment by about 30%. And similarly, in a musculoskeletal model, weakening the knee extensor muscles, which we often see in individuals with osteoarthritis, leads to increased trunk flexion as the compensatory movement. So our large and diverse participant pool enabled exploratory investigation in different study population subgroups. And in one such analysis, we found that trunk flexion angle actually differed across racial and ethnic groups. Because two of these groups were non-parametric, shown here are results from a Kruskal-Wallis test and a post-hoc Dunn's test. There have been very few studies examining difference in biomechanics across races, but in a recent study, Charisse Hill and colleagues found racial differences in gait mechanics. And they concluded that equivalency in gait measures between racial groups should not be assumed. And our hypothesis is, or our finding is hypothesis generating, and more studies need to be carried out to better understand these differences. But similar to the conclusions of Hill, we can't assume similarities between different racial groups, and future studies really need to make racially diverse study samples a priority. And I'm optimistic that these types of digital tools can help do that. We also found that in individuals 50 years of age and older, greater trunk acceleration was associated with higher mental health. Maybe these results indicate that people with higher mental health are more willing to stand up quicker or are less stiff in their upper body movements, leading to higher trunk acceleration. But this is entirely speculation, and similar to our analyses comparing kinematics to ethnicity, these are exploratory and hypothesis generating. But it is really exciting to see that there may be some relationships between mental health and the way we move. So while it was exciting to see all the places and the ways that people perform this test, this inconsistency was also perhaps the most significant limitation of our study. So not all participants kept their arms crossed in front of them or appeared to do the test as fast as possible. All the chairs were of different heights and cushioning, and camera recording angle, height, and distance also varied. In our study, we asked for participant feedback about their experience, and I think that this, in combination with input from experts in user experience, will be really helpful for making digital tests more consistent and usable in the future. So in summary, we ran a large-scale nationwide biomechanical evaluation of lay people at home using commodity cameras through our web app, which collects and automatically analyzes videos of the sit-to-stand test, meaning that even my parents, like my dad shown here, could participate all the way from Ohio. My mom was recording this, so I can't leave her out either. And these at-home recordings contain signals predictive of the presence of osteoarthritis and other health measures. And overall, the study shows that digital biomechanical analyses are possible and have the potential to become a supplementary endpoint for clinical trials and even an at-home health monitoring tool. So this study was just accepted to present at the World Congress of Biomechanics this summer, and the manuscript is in preparation with co-first author Łukasz Kaczynski, and the data, code, and website will be publicly available upon publication. So while we evaluated trunk lean and trunk acceleration because they were the most common parameters of previous studies, other researchers may want to evaluate other kinematic parameters or some of the other survey measures that we collected. And we are still collecting data, and in fact, thanks to Marcia Stefanik and Abby King for recently sharing the study with their cohort of older women, we've had many new participants over the past few weeks, and we're excited to include them in our final analyses. So in summary, we developed a machine learning model to predict knee loading from inputs that could be extracted from 2D video and demonstrate the feasibility of personalized biomechanical intervention with a smartphone camera. We evaluated the psychological construct mindset in individuals with knee osteoarthritis and found that mindset relates to physical activity levels and use of exercise for symptom management. We then created a mobile mindset intervention aiming to shift mindsets about osteoarthritis and exercise. And finally, we developed a platform to deploy a nationwide at-home self-guided biomechanics study. And with this large data set, explore new relationships between biomechanical parameters and measures of health and well-being. And throughout these studies, we primarily focused on knee osteoarthritis, but we hope that these digital biomechanical and psychological tools and methods can be applied more broadly to other diseases as well as the larger general population. So here's a summary of the journal publications that I've led or contributed to during my time here, including the 3 studies presented today. And I wanted to briefly mention the results of one of these studies that's related to the work I presented today, where Sean Zion found that mindsets about osteoarthritis are associated with future osteoarthritis symptoms. I've also had the opportunity to present my work at many conferences around the world, and it's really been one of my favorite parts of being a researcher. And I also wanted to mention one of these studies where we found that we actually saw a more adaptive mindset about osteoarthritis was associated with a larger reduction in pain after a year-long foot progression angle modification intervention. So I'm excited to share some of my ideas now on future work. So again, the mindset studies presented were just associative, and in the future, I'm really excited to see if we can leverage influencing mindsets in biomechanics for optimal intervention, compliance, design, and outcomes. On the other hand, we may want to understand how biomechanical interventions may be influencing mindsets even unintentionally. For so long, medicine has really focused on healing the body, but if we can integrate the mind and the body together, I really believe we can have the greatest impact on health and well-being. While in our studies, we only evaluated self-reported health outcome measures, our digital tools have the potential to integrate with objective measures from other mobile health toolkits like step count and heart rate. And I'd like to see digital biomechanical measures combined with other biomarkers to give a more holistic and insightful understanding of a person's health. And then it would be really exciting to see these different biomarkers feeding back into the intervention such that they are both personalized and adapt over time. The limitations of the studies presented today can help guide and inspire the next generation of digital biomechanical assessments. So in the future, we'll want to go beyond just joint angles and obtain mobile measures of muscle activations or internal joint forces. And we may be able to do this by improving and implementing 3D pose estimation and integrating that data with musculoskeletal models. And then, for example, rather than predicting the knee adduction moment from a neural network, we could actually estimate the internal knee loading from a personalized model. In conducting large biomechanical data sets in combination with other types of data, we should continue to lean on developments in statistical methods to understand, combine, and glean insights from these high dimensional and heterogeneous data. In our sit to stand study, the pose estimation algorithms showed less accuracy when people wore loose fitting clothing, such as sweatpants or skirts, or if an individual had a higher body weight. So we can also use our larger and more diverse data sets to develop or retrain less biased algorithms. And then finally, the interdisciplinary nature of my thesis work was really instrumental in all of the studies I presented today. And I believe that the future of rehabilitation lies in this interdisciplinary approach to digital health intervention and monitoring. So this includes disciplines such as computer science and psychology, but also experts in user design and experience, human-computer interaction, and public policy, as well as clinicians, coaches, and physical therapists, and perhaps most importantly, the people and patients that we're trying to help. By making biomechanical assessments scalable and blending these advancements with insights from other fields, we can move closer towards using biomechanics as a marker for health and well-being. And in doing so, we can help others move in the best ways that they can and continue living active and fulfilling lives. So thank you all so much for listening. I'd love to acknowledge some of the people that have made this work possible. This is probably the hardest part of putting my defense together because there's just so many people to thank in so little time. And none of this work would have been possible without the support of many, many people. And so I'll just be sharing a few of these acknowledgements now. First, I want to give a huge thank you to my committee. Scott, I could not have asked for a better mentor, advisor, or role model than you. The number of times I've cried in your office would probably scare off anyone else, but you stuck with me. And like you mentioned, much of my confidence as a scientist today is really due to your encouragement and support. And whether about science or life, you always knew exactly what to say to refuel my passion for science and to work towards the bigger picture. So I've also been inspired by your passion for serving through science, and that's made a tremendous impact in my life, as well as anyone who's had the pleasure to work with you. So thank you. Ali, thank you for accepting me with open arms into the world of psychology. Thank you for always challenging me to think so deeply about my work and make sure that it truly has the biggest impact it can have. In talking with you, I always felt very heard and supported, and for that, I thank you. And you've truly been an incredible role model and mentor for me, and I feel so lucky to have you as a mentor in my life. Nick, the input from you, from your perspective as a surgeon, has really been instrumental in all of these studies. So thank you for your support and enthusiasm. I always remember when I first sent you an email asking for your advice, and I immediately got an email back saying, here's my cell phone number, I'm free right now. And that rarely happens with anyone. I'm more or less an orthopedic surgeon. And from that initial conversation, I was just so inspired and excited to make sure that the work I did had a real and tangible impact on people. So thank you for being a huge part of that. Ellen, your lab was actually one of the first ones that I rotated in during my PhD. And while it was mainly based on your incredible work, when I first saw you walking in your cow print boots, I knew that I made the right decision. And something that really stands out to me is when I wanted to start National Biomechanics Day at Stanford, and you were the first person that was in our corner offering your support. And it really made a big impact on me and the value of outreach in science. And I've been really glad that through the Human Performance Alliance, I've been able to continue to learn more about your work. But thank you for being part of my Orals Committee. Abby, I've been so inspired since meeting you and seeing how you don't shy away from large societal challenges. And instead, you find a way to leverage the power of the community, of policymakers, and scientists to not just make the biggest scientific advancements, but to also see them through into their implementation in the world. So I'm really grateful for all I've learned from you about that and for the Catalyst Project for bringing us together. And thank you so much for being my defense chair. I've had the honor of working alongside so many incredible scientists. So shown here are the many co-authors of the studies I presented today. And I wanted to mention 3 co-authors on another paper where we investigated the effect of eccentric strength training on sarcomere and fascicle length in the hamstring muscles. Glenn, Patricio, and Martino came here from all over the world to work together on this. And I wanted to share a video of the first time we were able to measure sarcomeres in the hamstring in a live person in real time.
Oh, my days, look at that. Oh, wow. She's so excited.
I really was. And I've been really thankful for the opportunity that I've had to learn a range of technical skills and for these 3 scientists for making that summer so fun. I've had the privilege to learn from many incredible mentors during my time here, and shown here are just a few of them. So Jen, so look in the camera there. I just want to say thank you so much for your support in these projects. I truly wouldn't be here without you. You always find a very thoughtful way to make me be the best researcher that I can be, and I've enjoyed all the laughs and good times along the way. Scott, thank you so much for being such an incredible mentor and friend, and I'm really grateful for all that you taught me, as well as that you not only took many practical jokes in stride, but you were never afraid to dish it right back, which led to both a very fun and productive teamwork and experience, which is my favorite kind of teamwork. Łukasz, thank you for being my partner in the Moonshot division of the lab. I've never met a more optimistic person in my entire life. And every interaction with you, I leave happier and more inspired and excited. So thank you so much. I wanted to say thank you to Amy for teaching me not just about engineering, but also the International Society of Biodiversity, trips to the zoo, and many hikes. And I'm really thankful for our friendship. I want to say thank you to Rachel for always being there through the ups and downs of grad school as a colleague and friend. And thank you to Julie. You and Scott were the ones who gave me my first tour of HBL, which I still remember. And so I just want to thank you for your guidance and creating such a wonderful environment in the HBL. Diane, thank you for always taking care of me and the entire lab, both logistically and emotionally, and for telling me that I'm not needy, even though I know that wasn't always the case. Your dog photos and your emojis always brighten my day, and I know that if I ever needed to pick me up, all I needed to do was walk by your desk, and so I'm so thankful for you. I've had the opportunity to mentor some incredible students, and I wanted to say thank you to Andrew, Kaylee, and Angeli for their support with these projects and everything that they've taught me along the way. And I know I wouldn't be here without my undergrad mentor, Brian Davis, who has stuck with me as a mentor throughout grad school as well. You are the person that has helped me find my beginnings as a researcher, and your encouragement and advocacy is really the reason I'm here today. So I'm very grateful for you. To my Nimble family, I don't know how I got lucky enough to be in the best lab in the entire world, but I'm really grateful for the inspiring people and research team that make it all up, and all the good times we've had in and out of lab. To my elders, Apurva, Carmichael, Jenny, Chris, Scott, Nick, Kara, and Hannah, you were the ones that made my decision to join the lab so easy, because when I thought about the type of person and scientist I wanted to become at Stanford, I saw you all. Chris, Kevin, Hannah, and John, thanks for being the best dancing buddies, and extra shout out to John for being my neighbor both in lab and in Ohio and making those trips back to the Midwest so much fun. And thank you to all of our other lab members for making Nimble just such a wonderful place to work. I wanted to say thank you to the Mind and Body Lab for so warmly welcoming me into your family. I've always had an interest in psychology, but thinking that I knew something about the science behind psychology from the colloquial books that I was reading kind of made me thought about the time that I should join the cross country team because I could run a mile. And while I really could have felt over my head at times, I really wanted to thank you all for teaching me the depth and rigor of psychology and doing it in such a positive and supportive way. I wanted to give a huge thank you to Sean for always being one step ahead of me in the development of his mindset intervention for people with cancer, such that I always had someone to go to for help. And the incredible impact of your work is a large part of what kept me motivated and inspired to keep going with our intervention. And then another giant thank you to Chris for being my mindset intervention buddy from the start. And I'll always remember those energizing brainstorm sessions on whiteboards in the basement of the engineering buildings. And I'm beyond grateful for your support, both in research and personally. I wanted to say thank you to all the participants in my studies, both in the final state and in the pilot tests, many of which are here today. None of this would have happened without your support. And thank you to the many of people with osteoarthritis who so openly and kindly share their experiences that significantly contributed to the development of our studies. I've been part of a lot of wonderful communities during my time here. So the International Society of Biomechanics, as Scott mentioned, has been a huge reason that studying biomechanics has been so much fun. And I couldn't imagine a better international scientific family to start my career with, and everyone there. Thank you to the Hungry Kitten Club for being the dance family that I never knew I needed. Dancing on parking decks with you with a bunch of incredible women has been the best way to start Sunday morning. So I'm sending you sparkles to those who are watching. I had the opportunity to work with and learn from an amazing group of people at Kaya Health, and I wanted to thank them for teaching me what it really looks like to create a digital tool that's in the hands of users. To the Boom team, our little podcast family, we couldn't be what we are without you, and it's been a real pleasure to work with and get to know you all, and I'm really excited for the future of Boom. And on that note, I have to give a special thank you to Hannah. Yeah, I don't think I can look at you. Thank you for yes-anding me in all parts of my life, with the most memorable being the time I wanted to start a biomechanics podcast. And those times in the studio have really been the best times of my grad school career. And anyone who knows you just knows how you brighten up the whole world around you. And I'm so grateful that you've brightened up my life from the moment that we partnered on that 485 project together. So thank you. To the Baumgartners, my California family, what could have been a normal job quickly turned into a home for me here. Nick and Alex, thank you for making me laugh and keeping me up to date on the latest TikTok trends, even when you were supposed to be doing your homework. And Walter, thank you for your generosity and being the best wine and cheese partner. And Melody, your guidance in my life and my mindfulness journey just means more to me than I could ever express. So thank you all. Thank you to my forever friends, Casey, Audra, Kelly, Brian, and Brooke. Thank you for putting up with my shenanigans, listening to my 10-minute long voice notes, and always picking up the phone when I need a friend. I love you all so much. Thank you to my past roommates, Caitlin and Jasmine, for making the first half of grad school so special, and to the entire BioE cohort for the many fun times. And I felt really lucky to have gone through grad school with such a fun and incredible group of people. And thank you to the BioE administrators as well for all of their support. This couldn't have happened without them. To my current roommates, best friends, husbands, and fathers of our furry little boy, Bauer and Thomas, I literally don't know what I would do without you. I knew from the second I met you on interview weekend that I could not go another second in my life without being your best friend. So thank you for being my friend, making me laugh until I cry, taking a million photos with me, and making our house a home. There's really no one else in the whole world that I'd rather share that home with. So thank you. It's a really, really special thing to grow up so close to your cousins, aunts, uncles, and grandparents, your entire family. And I wanted to thank everyone for always allowing me to find home through your love and support. And I'm really grateful that I can always be my truest and weirdest self when I'm with you all. And somehow our insanity just keeps me sane in a way that like no one else in the world could understand. I think everyone here knows that going home was just so important to me, and it really kept me grounded through this experience. And I love that every time I went home, my family made a huge effort to all get together and to see me, and that just means the world to me. So thank you. I couldn't dream up a better family. Jen, thank you for being the best sister I could possibly imagine. Thank you for teaching me how to stay in touch with my creative side, how to be brave, and how to make everything a little bit more fun. I know I'm supposed to be the older sister, but I look up to you in so many ways, and I'm thankful to know that no matter what, we always have each other's backs. So thank you for everything. And Mom and Dad, thank you for not only supporting me, but for being right there with me through everything, even if that took us around the world, climbing the bridge in Sydney, Australia, and me and my mom kind of crashing a bar crawl that we weren't invited to in Dublin, Ireland there, having a great time. So I'm so grateful that I've been able to experience so much of this journey with you both. Mom, thanks for risking your perfect teacher attendance to come out and take care of me during my multiple surgeries. And we always joke that in bioengineering, I fell right between my dad as a software engineer and my mom as a nurse, but it doesn't begin to cover all of the things that I am today because of you. So thank you for being the best examples of working hard, serving others, being creative, especially with Halloween costumes, and doing it all through fun and through love. I love you all so much. So thank you.
Very much, Melissa. That was great. Melissa continues to break records at Stanford. That's the longest acknowledgement.
Sorry.
So I'm not kidding. Very lovely.
I cropped it a lot.
We have time for like one quick question. We have a closed exam where everyone has to ask some questions and then say, wow, what she's doing. Okay, so one or two quick questions. Anybody? Go for it.
Yeah. Yes. Thanks.
I was really excited about the mindset curriculum. Are there plans to roll that out either major qualifications or continuing up first? It's a great thing that it's going to be.
Yeah, that's a great question. So, so she asked what the plan is for the mindset intervention and disseminating that. So our next steps are to test it in a randomized control trial, and our plan is to integrate that with a digital therapeutics app to test if it does improve physical activity and engagement with exercise. But our plan also at the same time would be to develop some website that could be freely accessible to anyone. And then I think working with doctors to figure out then what would be the best way to direct somebody to that site or help get them enrolled will be important in figuring that out. But yeah, definitely plan to do that. Yeah, Dennis.
Continuing on that, do you have any like insight on how long that intervention like lasts in terms of like, is it, you know, for a couple months or years with the patient, or is it just have to be like 10 days or something?
Yeah, so right now it's just a self-guided, and during the pilot, we gave participants a week to complete it on their own. And some participants just finished it in like an hour and a half, and other participants did like a module a day, which is what we suggested. But then as of right now, it does end after that, but we got a lot of feedback from participants that they'd love either like reminders of it, for us to potentially add other modules. So we got a lot of ideas for, I think doing a longer term study will help us know if we do need to sort of do things to reinforce over the long term. So hopefully we'll get more insight to that in that study.
Thanks very much. Everybody, time for a quick high five.